Is it live? Let's see. Okay, seems to be live. So if it's live, welcome everybody to this experiment. And I'm getting my bottle of water. And let's see if all the technical stuff are working, which is probably going to be the goal for today is having everything technically work. That would be already amazing. Okay, so that's there. This should be a chat if it's working, and then let's see. Okay. Very good. As expected, there is nobody yet, which is again part for the course. Who's going to be interested in this? We'll see. Okay, so let's check that this works. And this works exact. Oh, okay, so there is somebody. Thank you for yes, thank you for the compliment. Okay, so let's get started. So I am doing this experiment as essentially trying to see whether people are interested in any of this. The reason why I'm doing this is that I have certain tasks to accomplish, and hello, and the oh no, there's more people joining. I think there's gonna be a delay between things that I see in the chat and my response. So anyway. The point will be that I need, there's something that I need to do, and this is a good way to force myself to do it, because now I have a public appointment and I have to do it. And what I need to do is the following. I have in this book here, we have already the whole part of reverse physics for classical mechanics. Where is it? There you go, classical mechanics. And so if you don't know how this works, is that, you know, for example, you go to this chapter of reversing Hamiltonian mechanics, and we see that we find a bunch of different conditions, like displacement field is divergenceless, like Jacobian if time evolution is unitary, and so on. And so we find that all these things are equivalent, and then we can basically map all of classical mechanics and all the pieces that we need to do. So I need to do the same thing for quantum mechanics, and which basically means I have a lot of ideas that are already in my head that I need to put down and make sure that everything is working and makes sense. And so I thought I would just do it as a live stream, because I do have a bunch of people that have contacted me. I'm a student here, I'm a student there, I'd like to contribute to the project. And this could be a source of pieces that people may contribute, because there's a lot of work that needs to be done. And so maybe somebody can even provide figures, or help me shape the arguments, or even check that my arguments are good. You know, double checking is always useful. So I thought basically you're going to see me working on this latex project, and the goal for today is to essentially create a table of content that basically is sort of the trace that this chapter should be, and make sure that I'm covering all the pieces. So we'll see how this works. So the first thing that I need to do is to create the files, and in usual tradition, I will just copy all the files, rename them, and delete all the stuff that is not useful. So quantum mechanics, and I'm sharing only the latex because I don't think that anything else really needs to be shared. And I'm just creating two files here, and then we are going to be able to go on the other side. Quantum, oops, fat finger. quantum mechanics. Okay, so this is going to be the chapter itself. Okay, so I assume, I hope, no, I should actually do this now. So I hope this is readable in some sense. And this is going to be quantum mechanics. And this is all stuff that does not belong here. Okay, so this is the file where the text goes. Then I need the file to build that, which needs to do RP quantum mechanics, and remove all of this, and this is done. And then I need to add this to the book itself, and we're gonna add it into the experimental section at the end, which is, let's see, ensemble spaces, there you go. So before this, okay, RP quantum mechanics. Everybody from Kurt's project, I guess it was like a fortuitous coincidence that I had the live stream exactly on the day that Kurt released the podcast. So I really am glad that you guys enjoyed. Kurt is a very nice person to talk to. He's really doing amazing work. And I don't know how he can do it. I mean, I would never have thought that that you could put like 2.5 hour interviews of details of all these things and have 350,000 subscribers. This is kind of why I'm trying to do this, because maybe there is a market for this as well. All of us crazy people. Okay, so let's see. Let's do this, and now compiling, and this is going to take some time. By the way, is the text readable? I did some tests in the past week, because if the text is not readable, this is going to be basically useless. Okay, so we have compilation done, so now there should be a new chapter in here. There it is, and it's blank. There it is. And since we don't want to compile the whole thing always, we just want to compile this, which is going to be a lot shorter, and it's 1 page. Very good. Thanks, Andre, for the confirmation. And okay, so now I need to start thinking about what are the pieces that needs to be here. And this is the task for today, having an outline. And there should be in the book itself already some things. Let's see if there is anything that I like to bring over. There should be in the part of the road ahead of quantum mechanics. There it is. Yeah, I don't think I want to do it like that. This is the old part in the many years ago, at the start of this project in 2016, I made a sort of a blueprint paper where thank you, I didn't even put the mic. Okay, so this should be probably better. I didn't check the microphone level. Okay, thank you for letting me know. Okay, so basically this is the part in 2016 that we wrote this long blueprint paper just to see where the things could be done, and this is the way that things were done back then, but this is not good. This is gonna be reusable, and then this bit is probably gonna be reusable as well, and then I don't have anything. Okay, so yes. Okay, so what do we have? What we're gonna have? We are gonna have probably a review of a quantum of the mathematical formulation of quantum mechanics. And here already there is a problem, because there is the standard sort of the wave function way, which is postulates, and it really should be done on the rays of a Hilbert space. So that's one way. Then there is the whole let's see, quantum mechanics on phase space, which means Wigner functions and Husimi, which I hope it's spelled like that, and the other guy that I don't remember. And there is that, and then there is the one more focused on open quantum systems. So this would be the Lindblad master equation. So these in principle are all things that are going to be needed at some point or the other. Then the probably, so if we think about the postulate, right, postulates are states are rays in Hilbert space, and then inner product, observables are Hermitian operator. And okay, I'll leave the typos for another time. Inner product and Born rule, and then there is composite systems, which means a tensor product, and then there is the unitary evolution. Okay, so we are gonna need somehow to show that unitary evolution is deterministic and reversible evolution. Then we need to show that projections are processes with equilibria. All final states are equilibria. And that is comparable. Heck, this is going to be high to be us. This is gonna be because that's not enough of a condition. There has to be, and these are the open problems that I need still to figure out. So projection is not enough. We need compatibility with a unitary evolution. This basically, when you are in a block sphere, right? If you imagine the block ball for a single two-state system, you could have a projection on a plane, and that wouldn't correspond to a valid quantum process. So if you require that the projection is also compatible with a unitary evolution, then you're bound to project to the axis, and that's the type of projection that we want. And so it's I still need to understand what are necessary and sufficient conditions there, but in principle this should work. And then you should be able to say that a unitary evolution is a series of projections, and that basically some sort of solution to the measurement problem when you characterize the measurement problem as being two different evolutions. Here would be that you can see the unitary evolution as a series of projections. So you take the projection as fundamental, and then you make a unitary evolution out of that. And so that would be the way out to say there is only one type evolution. So yes, so a limit of infinitely many series of projections, and this I already have it done, so this is not going to be a problem. So that basically would cover kind of this and part of this. Then what we have? Okay, for the open quantum systems, what I need still to do, and let's put in question mark things that I haven't fully figured out. So for open quantum system, so we need to recover the CPT maps, which are completely positive trace preserving maps, and these are all the possible quantum processes that you can have. And let's see if I remember these things. Positive, no, trace, okay, so linear maps, because they need to map mixed states to mixed states while preserving mixtures. So that's one thing. Then trace preserving, because we have to map mixed state, well, we have to map trace one operators to trace one operators, so that means it's trace preserving. Then it's positive because the map because mixed states have non-negative eigenvalues, so we need to map positive eigenvalues to positive eigenvalues. And then this is the problem, is completely positive. We need, this is where I have no idea how to do it, we need a characterization of completely positive in terms of only the system without the ancilla. Again, this is a technical problem. When we define all possible maps, one of the key requirements is basically you say, I have a system, I put an ancilla, and then I evolve without doing anything on the ancilla, then the evolution of the system has to bring the composite system in a valid state. And this again introduces the ancilla. So it's a condition not just on the ancilla, it's on the system, it's a condition on the system composition. And I don't like that. I want a condition on the system. What is the system doing? And how is it then equivalent for the system, for the evolution of when the system? What is the ancilla? Ancilla, it's another system. So when you have when you want to describe a measurement process, you have the system that you want to measure, and then you make it interact with a probe. The probe is the ancilla, is this other system that you make the system interact with, and then sort of it goes away, and then you have the other system. And yeah, so the definition, one of the basic definition for open quantum system is defined in terms of another system, and I'd rather that works. Okay, can I update? Yeah, there is, yes. It's I can update this, but it's not gonna be formatted correctly because right now I'm not writing valid latex. So let me see. Let me see. I need to do this first. There you go. Yeah. So right now this is not gonna be. This is just a text here. It's not gonna be here. Okay. And still this is doing the thing where it's updating the other. Man, okay, let me see if I can. If I remove this and I compile this, when I compile this, is it still compiling the book? It's still compiling the book. I made the mistake of compiling the book once, and now, whatever, it is what it is. I think you mentioned reducibility is incompatible with in hidden variables. No, it's not that it's incompatible. It's irreducibility. Basically, say, well, there might well be structure below, but it's not gonna be something that you can access. And so the point is that, yeah, you can put the hidden variables, but all the explanation have to be done in a way that it's independent of the hidden variable. You can put whatever hidden variables you have, and they shouldn't matter. So if my let's say my atom of hydrogen or of carbon, which is more complex, right? For some particular condition, I can consider it irreducible. Then I really don't care what's inside, and I know that there is substructure, and we can actually go and look at the substructure. But for those particular cases where the assumption of irreducibility is valid, you should be independent of the substructure. So whether you have hidden variables, go ahead and put them, but everything that I need to do has to be completely independent from those. Okay, so we got this, and then there's going to be the problem of really recovering the space of quantum mechanics, the fact that we have a projective Hilbert space, and here there are the things where I'll need to really think about, because I don't think I have it yet. Or I don't have it in a way that I like. Recover Hilbert space. So there is one possible argument that basically says I have a set of ensembles, and then I can go from each ensemble. Let's see, let's make it simpler. Okay, so we can do, let's do the spin 1/2. Recover spin 1/2, because that's gonna be much easier. So spin 1/2. I can basically say I have the space of ensembles that is fully characterized by an average direction. Right? That means I have a system that is fully qualified by a direction, and then I make a statistical ensemble of those, and only the expectation of the direction is enough to define the system. So basically the argument goes, let's see, what are they called? Gaussian states are fully identified by average and standard deviation. Okay, let's put this as a series of boilerplate. So I say fully divided by average and standard deviation, and then you basically say, suppose we have Gaussian states of directions, and with standard deviation all the same, with same standard deviation. And now this should imply that the space is a ball, because that's the only thing that you have. And then I don't know, like, how much can we recover from this argument? I don't know how much can we recover? Then another thing is suppose so like a space of directional pure states. So this is gonna be the same. So the idea is I have a state space for directions in space, and then we have the argument recycle the argument that we have to be able to put a frame invariant distribution over it, and this basically should tell us that 2-sphere is the only symplectic sphere, and therefore is the only space. And here I think I would still miss why are ensembles why are ensembles the block ball. I don't think I have this part of the argument yet, but there should be a series of arguments that we can always use for the two-state systems. Okay, so this part needs to be recovered, and then the problem is going to be to generalize this to arbitrary dimensions. Yes. So for where quantum mechanics is failed, we have a host of other places where we can show failing, and even the hidden variable descriptions is going to fail. So the way that people try to, so if you're assuming that hidden variable are going to make quantum mechanics fail, you're basically going to say, okay, there is a finer grained description that it's underneath quantum mechanics, and therefore you need this finer level description to get the true what really happens, the basic law. The arguments that we're going to follow are go exactly in the opposite direction. Is like in a sense, classical mechanics fails because it's too precise, because it's making available some ensembles that are impossible to prepare. Like I can't prepare things that have an uncertainty that it's too small. And so quantum mechanics fixes that, because it fixes the fact that quantum mechanics is too precise to be physically realistic. And so what we expect is the failure of quantum mechanics will be of the same type. And so we don't want in the variables. We want to understand why you have the classical failure. And in fact, do we have in the book I don't think we have the classical uncertainty principle. Do I have the classical uncertainty principle in classical mechanics or not? Because that might be a good introduction to this part. Let me see. Do I have it? Infinitesimal reducibility. No, I do have it. Okay, so, and I have it in the old way. Okay, I have a better. Okay, so there's gonna be a to-do here. To-do review classical uncertainty principle. that might also be a good way. So anyway, that's why we don't want hidden variables. Hidden variables also would be different for each different system. The hidden variable of a hydrogen atom would be different from the hydrogen of a buckyball, and it would be different from the hidden variable of an electron. So I'm not going to be able to make a general theory of hidden variables, also because they're not measurable. So it's the ancillary justification of decoherence. In decoherence, that's how you get to the classical states. Is basically you take an ancilla, you make your interaction, you trace the ancilla away, and now you have a mixed state with higher entropy. And okay, so where do I put the classical limit? I have no idea. So classical limit, this we already have at this point. Classical mechanics is the high entropy limit of quantum mechanics, and the argument is going to go in this way. Find classical transformations that increase entropy. Show that they are all unitaries, and by unitaries here I mean symplectomorphism, unitaries, plus stretch of phase space. Find equivalent of phase space stretching in quantum mechanics. See that it is a CPT map only defined in the antinormal ordering. Show that it rescales the commutator by the factor of phase space stretching. Show that this is equivalent to the limit of h bar to 0. This is a video that that we put on this channel, and then I found somebody who actually came and helped me on some of the math, and that's why I'm actually doing this, because this thing of putting random things on YouTube and trying to find people that actually can help me on technical things has actually worked once. So that's good. Okay, so we have the classical limit, and so here it would be nice to yeah, okay, I don't know if I'm ever gonna be able to do those things well. Like basically, it would be nice to show that the equivalence principle is actually that. The equivalence principle, when the founders of quantum mechanics were trying to figure out what quantum mechanics was, and they used the equivalence principle as guidance, the insight should be that they were actually trying to look for a theory that would recover classical mechanics in the high entropy limit. And so the idea is that everyday objects like this, they're all high entropy, so you can use classical mechanics and you are good. So now what else do I need? Oh, the composite system. This is gonna be a pain in the butt. Yes, composite system. We have to show that essentially system composition of quantum systems that is itself a quantum system gives the tensor product. And Let's see, there should be, there was, oh man, wasn't there? There's something embedding, Segre embedding? Let's see, Segre embedding is using projective geometry to consider a Cartesian product of sets of two projective spaces in a projective variety. Yes. That's the thing. If we can get to the Segre embedding, that would be great, right? Yes, to their tensor product. Okay, so no, not here. Composite system. So there is basically, there will be review the arguments in the paper, see if using a Segre embedding would make our life easier. Who knows? What it means, first time attending, well, it's first time that we're doing this, so it's the first time for everybody. Okay, so let's see if this flows in any way. Probably not yet. So first we need to review all of this. And if I just have a review like this is gonna be horribly boring. And yes. So why don't I leave the open quantum systems for later? So we review open quantum systems here, and then we find, yes. When we talk about open quantum system, we'll define it and recover things and show in the reverse physics. First we give the equation, and then we see how we recover the equation. Yeah, there is this whole part that I need to figure out, and if anybody knows more than me. So there is the whole difference between, what are even called? I forget, the Krauss operator and the jump operators. How are they related, if they are? And then the other thing that I still don't know, what are the possible motions on a block sphere? That is, what are the possible vector fields essentially described by the Lindblad equation. So the Lindblad equation is essentially an equation on the space of statistical mixtures that tells you essentially how open quantum systems can evolve. And all of these things, the problem with quantum mechanics is that all of these things are really done just in a mathematical way, and they're really never done in a geometrical way where you can see things. And I want to see things. And the block ball is nice because it's three-dimensional, we can picture it. And so I want to be able to know essentially how this works is just a simple dynamical system, right? It's a dynamical system. So at each point of the block sphere, you're going to have a vector that tells you where the states are going to move. What are the possible evolutions that you can have? So I know that unitary operations are just rotation along an axis. You pick an axis and then you rotate around that. Those are the only possible unitary operations. And you can even generalize this to, at least for the three-state quantum system, you can still kind of picture it in some way. And again, it's all just rotation over rotations, like precession type thing. So that's the only motion that the unitary evolution allows. And the Lindblad operations are going to allow you, for example, to to have something dissipative. So something dissipative would move everything to the ground state. So if you imagine that you have the block ball, then as the block ball goes, shrinks to the point that it's the lowest energy, right? So that's it's sort of an evolution that it's allowed by an open quantum system. But there should be evolutions that are probably not allowed. So even talking to people that know these things more than me, they basically have the intuition that if you just take a plane, right, in the block sphere, you can't just move toward the plane. You can't have an open quantum system that moves towards the plane. And but nobody was able to give me a proof of that. And again, there should be a way to just prove this and say these are the possible motions, and then we can probably understand the completely positive requirement. Because the complete positivity is going to rule out some of these motions, and I do want to know what things do in that space, because I want to see it. And so this is an open problem for me to understand how, and it shouldn't be that hard. Okay, so the quantum system, we move there. Where do we need quantum mechanics in phase space? Oh, we should talk about the whole negative probability stuff. Where do we put it? Well, I don't know where we put it, but let's just start a new section. Negative probability in quantum mechanics. And then this is gonna be what's it called? Convex combination versus affine combination versus a linear combination. There you go. There you go. And for people who don't know this, so a linear combination is what you have in vector spaces. You have two vectors and you make all possible sums with all possible real coefficients. We're always talking about a real space here, so let's just put it here. And so if you have two vectors and you take that are linearly independent and you take the all possible linear combination, they form a plane. So the plane is the space spanned by two vectors for linear combination. If you do an affine combination, an affine combination is where all the coefficients sum to 1. So it's basically a constraint on the coefficient that they will have to sum to 1. And so if you now have two vectors, the affine combination is the line that connects those two vectors. So it's a subspace of the, if I have two, it would be a one-dimensional space, it would be a line. And in affine combinations, the coefficients can be negative. If you want the coefficients to be non-negative, then you do a convex combination, and the convex combination only gets the point in between. So if you have two vectors, the convex combination is the segment that connects them. And so when you do sort of a classical probability, you have a convex space. You have the points that are going to be, let's say, your state for a discrete system. And then you do a convex combination. So if you have three states, you have a triangle, and the triangle represents all possible convex combination, all possible probability distributions, right? And if you have two, it would just be the segment. So it's a convex combination. Now in quantum mechanics, when you have the state of mixtures, which would be sort of the full probability space of the theory, if I have two systems, I don't have a line, I have a ball, right? And so you can't reach the ball through the convex combination of two things. And you would need at least 4 points to get everything through an affine combination, right? Because 4 points with a constraint that everything sums to 1 becomes a three-dimensional space. So with 4 points, you get the full R3. And so if you have the block ball, you pick 4 points. Now, every point of the block ball can be described as an affine combination. It's not a convex combination because the block ball is not a tetrahedron, so you can't describe it with a convex combination, but you can describe it with an affine combination. So you have these negative values. And of course, it's totally unphysical. It's just a mathematical trick that that you have, but it's useful when you're doing quantum mechanics on phase space. So that part should really go there, because it really tells you what these negative probabilities are in quantum mechanics, are just a nice trick to get this thing going. So it should definitely be there. And what I want to say about quantum mechanics on phase space is basically, I think it's basically I want to say that that quantum mechanics on phase space is essentially using affine combinations, since convex combinations are not sufficient. And there is interesting details that can be explained here. Probably should make a video just on that. Okay, so we review. So how would this go? We review the things, and we say these are the postulates, and then I should probably start working on the postulates themselves. So the unitary evolution is going to be the simplest one, and so you say that. And then you are going to say, okay, but unitary evolution, but the measurements are different. And so what are the measurements? And you say measurements are going to be other things that move and do that. I should probably talk about mixtures here as well. So I'm going to talk about mixtures without talking about evolution of open quantum systems. That I think it's best. Okay, so I have unitary evolution, I have projections, and then I'm gonna say these are the limit of that, and that basically takes care of this and part of this. Unless I want to do the composite system first, because that's more independently thrown out. Yeah. Okay, so talk about the fourth postulate. Then you do this and you remove one postulate. Then you do this and you remove the other postulate. Then you do this and you remove part of this postulate, because I'm saying what things are. And okay, then projection as final state. This is a different thing. Okay, and now remains the problem of why do we have the Hilbert space to begin with. So this basically takes care of all the motions on the phase space and how to make the composite. So this would be the classical equivalent of, I told you what Newtonian and Hamiltonian mechanics are, I told you what the product spaces are, and that's it. And so we can leave the reconstruction of the proper state space at the end, like we did in classical mechanics. And then we can talk about the open quantum systems, because that would be the Newtonian analog of quantum mechanics. And then we can talk about this in terms of starting to figure out the space itself. And then I have to argue how to get to this. And this is going to be the hardest bit. Or should I do the classical limit first? I would do the classical limit after I've done this, because for the classical limit I will probably want to have the Wigner functions explained, and I will want to have talking about open quantum system, because I need to find the CPT map, and so I can do all of this without doing that. Okay, then let's see, other pieces that I might want to talk about. There is the whole thing about the Kähler manifold. Let's see if I remember that correctly. Kähler manifold. I even got the spelling correct. Amazing. And yes, so this is something that scalar manifold interplay of symplectic structure with basically the metric tensor can. Okay, so let's say let's see. This is not going to be a chapter. This is random things to look at to see whether they are helpful. There is scalar manifold, that thing. Then for unitary evolution is the risk of evolution. So this will gonna need multiple different conditions. So, but I will. Okay, so this would be like one possible way is a projection with 100%. But that's gonna be later anyway. All right, let's put all the 100%. Okay, measuring with. Yeah, but that's gonna be here. But that, you know what? Because we need multiple different conditions for unitary evolution. One is conservation of entropy. The other one is going to be conservation of probability, i.e. Like basically unitary evolution. Is there anything else that I can have as different equivalent conditions for this? Okay, so in quantum mechanics we also have preservation. In classical mechanics we also have preservation of uncertainty. There's going to be probably preservation of uncertainty. How could we do that? We are going to basically be looking for a map on mixed states. Yeah, that's gonna work, but I would need already the CPT map to make that argument, because I need to have a map that works on mixed states. I need to say that it's a CPT map, and then the maps, the CPT maps that conserve entropy are the unitary, but they would be here. So would require CPT. This is the nightmare of actually writing down the reverse physics approach, is that you have to always stay there and think what are the prerequisites to make the argument, but you still need to make the whole thing flow, but everything is connected, and so you have to unroll this thing. And from classical mechanics, it took me months just to figure out what was the correct order of things. So I think what's going to happen is that we start with something, we start to develop some sections, and the sections are going to be reshuffled around infinitely many times until we converge to something. Okay, so, well, that's the job that I set up myself to, so I have only myself to blame. Okay, so where was I? Okay, where was I? I have to relook. So, okay, we start the chapter, we're gonna say, okay, classical quantum mechanics is gonna be this and that. First we need to review the things, and then we are find necessary and sufficient condition for what a composite system is, and how do we get the tensor product, and then we are going to find necessary and sufficient condition for a unitary evolution, again given the other postulate, and show that basically we just need the deterministic and reversible evolution to justify Schrödinger equation and unitary evolution. Then okay, so here, yes, I assume that I can give I can put this here already. A series of continuous measurements. Because I already know what a measurement is in terms of postulate number 2. And so what I'm basically saying here is given postulate number 2, I can recover unitary evolution. I have something that keeps measuring something with 100% probability. And so I get that. Because even all of these are going to use the Born rule anyway. So I might as well use this for the Born rule. And then once I say, okay, unitary evolution is recoverable from the Born rule and so on, we remove the postulate. And then we basically say, okay, but now we have to justify why we have the projections. And now we need to justify the Born rule. Now, am I going to consider the Born rule as part of the state space? So the Born rule is equivalent to classical mechanics to the symplectic structure because that's the geometric structure. So recovering that is, it's part. I can't recover the Born rule by itself. I need to recover it with the full space because otherwise it just makes no sense. So here I can recover projections and I should be able to recover Hermitian operators. That's what I should be able to do. So observables and this is where I have to say that essentially convex maps of mixed states are observable, are Hermitian operator. This is the mathematical bit that I have to prove, because basically what I want to say, I have a space of statistical mixture that it's a given because I'm given it mathematically, and I know that it's this what is it? Unitary trace. Oh, Madonna mia! It's a space of mixtures of what is it called? Trace one Hermitian maps. I think I'm missing something, but anyway, those things. So those are my mixed states, and then I'm gonna have statistical quantities. That what is that? Now what is it? So density operator. Density operator. It's it's a linear operator. Oh, mamma mia! Positive semi-definite Hermitian operator. There you go. That's it. Yeah, it's the trace class, trace 1. Positive semi-definite Hermitian operator of trace 1. Something like that. Yes, positive semi-derivative of Hermitian operation of trace 1. There you go. That's the thing that I was. It's such. I don't know why we don't have just a mathematical name for that, but let's just call them mixed states. So that's the physical name. Okay, so convex maps on the mixed state. So I have the space of mixed state. I have a linear map, and it needs to be linear because if I make a statistical mixture, then the average has to sum. And then if I can show that those have to be Hermitian operator, then I basically say all the things that I can measure statistically are Hermitian operators, and then I'm done. And let's see, do I want... there is that whole other business of what eigenvalues and eigenvectors are. And I think I would do that here. There you go, quantum states as equilibria. Okay, so this is where we are gonna start reversing the whole complexity of the space, and we're gonna show that for a unitary evolution eigenstates are equilibria. That is, if I have a unitary evolution, the eigenstate is not changed. Therefore, it's, if you think it as a dynamical system, it's an equilibrium. The evolution is not changing the system. Good. And then you show that for any quantum state is an eigenstate of some unitary. Right. So, and this is where we do the reverse physics thing. We say one thing and then we prove the opposite. So this basically tells us all quantum states are equilibria of unitary. And then you can also show that with the same thing, all quantum states are equilibria of projections, so of measurements. And in fact, we need to show, when we say projections, we need to show that projections increase entropy. Better yet, they cannot decrease it. In fact, the projections cannot decrease entropy. But at that point, it's kind of silly to say these things here. This, I'll have to say it here, because I'm already talking about equilibria and that the outputs are equilibria. And so I want to say that eigenstates of projections are equilibria. And therefore, all quantum states are equilibria of projection. That's what I want to say. And then basically this should have a kind of the analogy to thermodynamics should be here. So context is like different ensembles, different type of ensembles. And this should be here. Okay, so, but I think the argument of quantum states are equilibria has to be done. Do I need it here? Because it's going to be useful also here, because a series of continuous measurements, I want to be able to say that this is a quasi-static evolution. So the point is that all measurements are basically some processes that increase entropy exactly like you have in thermodynamics. You change the boundary and do this. But the idea that you can change this boundary slowly, and if you change this boundary slowly, you basically have a quasi-static evolution. And so I should put it here that unitary evolution is a quasi-static evolution like in thermodynamics. I'm trying to take all these random thoughts and make them, put them in a consistent thing so that it looks like I thought about them in a very, linear fashion, which is totally not the case. Okay, so this is the piece. Okay, so now, why do I need this here? Because I wanted to basically have it as an introduction. Okay, YouTube is not receiving enough video to maintain a smooth disastro. Well, I don't know. YouTube is complaining. I don't know what to do with it. What is it? Is something happening or? What? I do not know what. Everything looks good. Thank you, because I get this alert from the page. I'll just ignore the alerts. Oh, first time of doing this. I have no idea what's going on. Anyway, okay. I'll go back because I completely lost my train of thoughts. Okay, so we start with this. We say we look, we review the postulate, we review what mixed states are. We get rid of the composite system, showing that if we just have a good definition of what a composite system is, you can derive tensor product from the other thing. So it's not an additional constraint, an additional physical thing. It's already implied. And then we do the same thing for a unitary evolution, that given the mixtures and entropy, there you go, because we're going to need to use the entropy. Given the definition of probability of the Born rule, of uncertainty, hopefully, and projections, we can define what the unitaries are in all these different ways. And then we're going to say, okay, now we're done this, so these two postulates are gone. And now we get to projections, and we say what projections are. And we say that, well, first of all, we need to understand this. Basically, we want to argue that projections are processes with equilibria, like a thermodynamic thing. And so projection itself is not enough. Projection basically means that if you apply the thing twice, you get the same results. So it basically means that all the outputs are equilibria of the process, because if you apply it twice, you get the same result. So that's basically how we get the projection. And then we show that the projections cannot decrease entropy, so we have this thermodynamic field to it, and eigenstates of projections are equilibria, and all quantum states are equilibrium projection. In fact, we can, this mathematically, this is what Hilbert spaces add on top of Banach spaces. So Banach spaces have a norm, and Hilbert spaces have an inner product, but requiring the inner product, it's exactly equivalent of having projectors for each subspace, which basically means in quantum mechanics is that you can measure every state. That's basically it. And so that's an interesting tidbit to put there. Then there is the analogy to thermodynamics, because the fact that there are only some observable well-defined is exactly like in statistical mechanics. In a canonical ensemble, what is it? Let's see if I can get it right. Canonical ensemble, the pressure is defined, the temperature is defined, and the chemical potentials are well defined, but then the volume is not well defined because it jiggles. The energy is not defined because it jiggles. Right? So that's the idea. Then you change ensemble. You go from canonical to grand canonical or whatever, and then you change what quantities are well defined. And so this should be the same thing. We want to argue that that's the same thing. And then, since we showed that unitary evolution was a series of continuous series of measurements, not a series of continuous measurements, a continuous a sequence, let's call it sequence of measurement. We are always measuring something. Then unitary evolution is essentially a quasi-static evolution, and this should make the parallel to S matrix calculation, where we put initial state at minus infinity, and final state at plus infinity. Yes, which basically for a process that actually lasts, I don't know, femtoseconds, I have no idea. Seconds, well, of course, in quotes. Okay, so we got that, and then we're gonna able to recover observables, and there is there. So I don't know if it's gonna be useful, but we should be able to note. Is it useful to note that any observable is compatible to some unitary? That is values are equilibria. Any observable is left unchanged by a unitary. This is something that I don't know whether it's kind of a physical requirement or not. Because the idea is that you know, if we have quantities and we're not able to keep them, you know, stable for some even infinitesimal time step, I don't know that they would make sense. So the fact that in quantum mechanics any observable have a unitary that have a process that keeps that value the same seems meaningful to me, but I don't know what to do with it. So I'll just put it there as a comment to see if I can do anything with it. Okay, so up to here, then we would have all possible motions except the open quantum systems, which are basically the bridge between the unitary and the projection. And then the idea is that once we get that, we would recover everything. And now we have, and now I said that I need quantum mechanics on phase space to do the classical limit. Do I need though? Because it's nice to see that the Wigner function reduces to the probability distribution, and that the Wigner, the Hussiming, and the third one that I don't remember. I should just go and look up the name of the third ones. Husimi distribution. What's the name of the third one? It's where is it? Where is it? Oh, the P. There you go. The Glauber Sudarshan. Mamma mia, all these names. Where was I? Okay, so I don't know if you guys know what these things are. The Wigner function, the Husimi, and the Glauber Sudarshan are basically ways to represent quantum state and especially quantum mixtures in terms of distribution over phase space. It's just that these distributions in the Wigner and the non-negative, it's positive defined, and but the issue that you see me is that it's like the pieces are not independent, so it's a little bit harder to make a nice parallel with statistics, but still you can recover the observables, the averages of the observables as integration over these things. And these things are really used a lot in quantum optics. And yeah, so and there are three of them because in quantum mechanics you have different products, right? If you change position and momentum, you permute the powers, you get different products. And therefore, whenever you're doing a representation of this type, you have to fix the operator ordering. And there are different ways to do it, and these are the three standard ways to do it. But anyway, so we got that, and then we're gonna say that these what this thing is. And so the question is, should I put the classical limit before that? Because at the end of the day, I do not need, right? Because I'm doing the space of transformation. It's just going to be an open map. I do not need it. So I'd rather do the classical limit before, because then we can relate the classical limit to open quantum systems and all of that. So you're basically saying you increase entropy, measurements are going to increase entropy. So however you increase entropy, you get classical mechanics, you don't care how. Then negative probability starts becoming how we describe these states and what are these states. And so I can also show that these are useful things, but they don't really fully characterize the space. Then we're going to have the quantum states are equilibria. And what is going to be the argument there? I have no idea. Then we have these pieces for the... Oh, there is the whole thing about the infinite dimensional space. Okay, so... Okay, so at some point I need to problems with infinite dimensional spaces. Part of the problem of fully recovering quantum mechanics is that we don't have the right math to handle the infinite dimensional case. And for example, one of the things that so unsuitability of Hilbert spaces. And so here there are a bunch of problems that you have for Hilbert spaces. Hilbert spaces with different number of degrees of freedom are equivalent. So basically, if you take the Hilbert space for a single particle or a Hilbert space for 10 billion particles, all of these are separable, and mathematically they're exactly the same space. There is a unitary transformation that goes from one to the other, and it's like it's a change of coordinate from going from one particle to a billion particle. You can create a process that encodes the state of 1 billion particles into the state of one particle. All of these things do not make sense, and they're not, it's not like that in classical mechanics. In classical mechanics, the space of 10 billion particles is different than the space of one particle. So, good. And this is not the case for Hilbert spaces, for quantum mechanics, which tells you that the space is not quite the right one. Then the other thing that it's a problem, it's problem of ill-defined expectations. So for example, you can have states with infinite energy, undefined position, and so on. This is the document. What I'm writing is the thing that at some point will become the chapter of the book. Right now it's just a skeleton. So okay, so that's a problem. Let's see, what other problems were there? Okay, that's basically, you know what, there's a to-do. We just have to take all the arguments from the paper. There you go. And then we can basically have the suitability of Schwartz spaces for special case, and that's it. So that's the only thing that we can recover is actually that. And now we need so how am I going to do that? This is an open okay, that I'll need to figure out in the coming weeks or months. Okay, so So all the problem is still how to get to the projecting Hilbert space. So once we have the projecting Hilbert space, getting to the space is not a problem. And we can also see if there is anything of the old arguments salvageable. That's another question. Yeah, then there are the other potential arguments that other people have made, and maybe there is stuff that we can steal from them. See if there is anything we can get from GPT or other reconstructions. The problem there is that a lot of those things only work for finite dimension. So that there are a lot of reconstructions that have this idea that you have you basically say states are probability distributions, and you have two dimensions. Like one is the dimension of the physical distribution itself. And the other one is the dimension of the probability distribution that you can take out with a measurement. And then, for no apparent reason, you say that the one that defines the state is double the one that defines the outcome of a measurement. And then, lo and behold, you get quantum mechanics. So, of course, that thing is not... I don't know, it seems like more mathematical tricks that is not going to work in infinite dimension, because in infinite dimension you still are going to have the problem. Infinity times 2 is still infinity, so it's there is no double in that case. There is still a sense that there is a symplectic structure there. There are two variables that are incompatible, and so I don't know if there is an argument that can be constructed from there. And no, there is also the arguments that Rovelli was using, but yeah, so I think this is the part where I need to think more about, but all the part up to here, like all this chunk is basically just writing. Because all the arguments there are things that in some way we are already done, and they are already in my head, they just need to be written down. And probably while doing those, we are going to be able to see better what the pieces that we need for this part are. So I shouldn't worry too much about this part, because I already have months of work to do. So shall we call this part done? Yes, probably we can say, I'm not going to have a perfect outline anyway, so it's probably this is enough to start. And thanks, Steve, for, I'm glad you liked the interview. And a lot of people, I think, that they came and gone and went from the interview. So there are 9 viewers, but I don't know. I think it's always different people that that are recycling. As I said, I don't know how much. Is this any interesting, or I have no idea. So okay, so what should I do now? I could either stop here, since this was already an hour and a half. And then basically next week I'll start working on one of these things. In fact, what I should do is GitHub, it would be a commit and push, because that's how all these things should end, with a commit and push. Let's see, so I'm not gonna change this. And then let's put quantum mechanics, adding outline, commit and push. Okay, so I'm done with whatever I wanted to do. If anybody has random question that wants to ask, feel free. I'll wait for a minute, and if there are no questions, I'll just end. I don't think there are going to be questions. Well, thank you, Tom, for for listening to me rambling for an hour. Yeah, so I'll keep doing this and see what happens. Thank you for all that you have joined. And oh, random question. There you go. Can we define differential equation on distribution instead of functions? Yes, we should be able to. So in principle, yes. I don't know what is the correct math to do it, and I don't even know if it's a solved problem in mathematics. But in principle, so what is the issue? Is that you are basically having distribution and functions are infinite dimensional vector spaces, right? And so where the spaces where you define a differential equation are basically finite dimensional spaces, and so it's just a matter of knowing how to extend these tools in the infinite case. And some of them, for some of them you do, because when you do, let's say, entropy maximization, you're basically doing that. You're doing some type of, finding a maximum, right? You're calculating some second derivative of the functional, and you're doing that. And same thing when you, in field theory, you do your action on a field. That's essentially what you're doing. You're varying the field. You have a function that it's a function of a field. You do some variation, and you do. So in principle, yes. And whether there exists a full general mathematical theory for doing that, I have no idea. I really don't know. And then Steve is asking, would you be interested in condensed matter analogs of Bohr rule? Yes. How do they look like? They're like Bohr rules on density matrices? Is that how it works? And this is where you see the delay from me speaking and then the message coming back. Wow. Talking about lag. Okay, so it's impossible to have sort of a live conversation with the chat. Interesting. Okay, that is. What about constructing a fermionic stress energy tensor for Ash? So the whole thing of Einstein fields equation, that's something that I don't know how to do it. Like what I know and what I understood is that the stress energy tensor can be understood as the variation. Okay, there you go. Thanks, Steve. For the stress energy tensor, what I understood is that it's the variation of the Lagrangian with respect to the metric tensor. And the metric tensor, we know what it is physically, and we have a geometrical and physical interpretation of the Lagrangian. And so it could be that we would have 30 seconds delay on live chat to video. Okay, good to know. what do you say? I get distracted. Let's say I have a problem of reading the chat while I'm talking. Is that I get distraction? Okay. Anyway, so the point is that essentially I don't have yet a good understanding of general relativity because I also don't have a good handle of how to do things in classical field theories in things that are precise. Because what I basically need to be able to understand what the stress energy tensor is and so on is to have a generalization of Hamiltonian mechanics, which means symplectic geometry, for the infinitely many degrees of freedom. And in math, I haven't found such a thing. In fact, I found people trying to do this and sort of giving up because they weren't able to do it. And on the math, on physics side, we do it. I mean, because we do have Lagrangians and Hamiltonians for field theories, but there are multiple ways to do it. And I don't know yet what is the correct way to do it. And until I figure that out, I have trouble understanding what then a Lagrangian is, what is the generalization of the geometrical and physical interpretation of the Lagrangian that we have for classical mechanics is for field theory. But if we were able to do that, then we would understand why the Ricci tensor is the Lagrangian for a free field, for essentially for gravitation, for when there are no energy fields, when there are no other fields. And then we would also understand what exactly is the stress energy momentum tensor. So my hope is that once you do all of this, you have a physical meaning of why the curvature is important in terms of keeping track of states and number of configurations, a number of degrees of freedom, and essentially entropy on field configuration. But I don't have any of that. Okay, so let's see if there is anything on this particular topic. Yes, stochastic calculus actually when I was trying to figure out how to put measures on function spaces, most of the mathematicians would tell me, oh, it's impossible, it's impossible. And then I talked to people who do stochastic processes, and they said, oh yeah, we do it all the time. So there are some measure theoretic things that probably people that do stochastic processes and stochastic calculus is going to be some generalization of that, know how to do. So, and Tom says, I am of the opinion that missing self-energy tensor in GR is a problem. No one can make a covariant one. Ah, okay. So I don't even know. I'm not a GR person, so there are a lot of details of GR that I don't know. So yeah. So right now I'm concentrating on making classical mechanics of both classical, particle mechanics, so both classical and quantum mechanics work in some sort of a general way with and then I'll figure out field theories when everything else is done. Then let's see. Okay, then Santiago, why don't we focus on explaining some experimental data about a chemical reaction? Because right now I'm doing other things and I can't do everything at once. And then Steve, because of the Bohr rules, the present wisdom details require tracking of vacancies in crystalline lattices and with a constant standing wave in that lattice. Okay, I probably won't be able to understand much of what you're going to tell me, but try. So if there is a generalization of the Bohr rule on essentially on mixed states, because the Bohr rules is typically on impure states. But I would think that it should be just some trace of the products of so some kind of distance between things. Perhaps an email chat will allow for more time to type of shares. Thanks for your open. Okay. Yeah, thank you guys for staying. As I said, I was expecting to to be essentially by myself, and I said to myself, if there are no major technical issues and there are 2 people following, it's a success. So I think it was a success. So I'll do this again next week. And if there are no other comments, I'll have to wait 30 seconds because we said that that's the delay. If there are no other questions, I'll close. If we know that the underlying things of quantum mechanics is field mechanics, should we start with a classical field theory? No, in the sense that the way that I see quantum mechanics is essentially taking distributions that you would have on a classical phase space on position and momentum, and then essentially capping the lower bound of the energy to 0. That's essentially what quantum mechanics is doing. And so it's still a particle mechanics theory because the state is still fully identified by the expectations of position and momentum, right? So it's a field theory in the sense that you have a distribution of those things, but that's true in classical mechanics. In classical mechanics, when we do reverse physics of classical mechanics, we derive all that we need by saying we have a distribution, space of distributions over phase space. So it's exactly analog to what you would have in quantum mechanics. So our approaches are sort of very in parallel and in sync. For field theories, what happens is that the full state of the system is determined by all the possible polynomials of all the expectation values of all the possible fields. And so that's what you're really describing. So in classical mechanics, again, the point, the full state is the field configuration, the perfect value of all the possible field configuration. And that's the state. But again, if we were to do an approach that is similar to what we have for classical mechanics and quantum mechanics, the real object is not the field, perfect field configuration, because that's not reachable. It's uncertainty, it's distributions, probability distributions on those field configurations. And that's where the mathematical part is hard, is that I don't know how to describe those things. I don't know what is the correct way to mathematically do those things. And I don't know that there is one already well developed. I think that we have hodgepodgey things from the physics and mathematicians, my sense is that they have been trying to do something that it's too, how can I say, that tries to do too many things, and we need a lot fewer things in physics. And so they haven't been able to do that more, more complete part because it can't be done, and in physics we don't need. So I think we are in kind of this hybrid. So and then if everything works out, that same theory of probability distribution over field configuration gets quantized and becomes quantum field theory. And so you have this you should have this perfect correspondence between the two. So essentially, to recap, mechanics is identified by finitely many degrees of freedom, where by degrees of freedom we mean polynomials of position and momentums, and you only have finitely many position and finitely many momentum. In a field theory, you have instead infinitely many values of the fields and the conjugates of the field. So we should start with particle mechanics for quantum mechanics. I hope this wasn't too long. I'll wait the extra 30 seconds and let's see. Okay, I think we're gonna close it. Thank you again for everybody who stayed here, and see you next time. Bye.